So the recorder is on, and alrighty. You guys ready? Okay, we are ready to get started. Okay, yes, I need you guys. All right, thank you. So let's go ahead and get started. This is where we left off. This is where we left off last time on Tuesday, and we were just talking about comparison, especially the last one. The last one is the tricky one because when you want to compare for equality, if you use a single equal symbol instead of double equal symbol in C and C++, or Java and other C-derived languages, then weird things will happen because in C and C++, you can actually have an assignment operation specified as a part of a condition. Okay, and that, I know it doesn't seem to make any sense, but C and C++ were originally written by hackers for themselves. Now, when I say hacker, I do not mean a black hat. I mean, somebody who just likes to tinker with stuff and write programs and get things to work. And those were the first people, the two people who wrote the Unix operating system. So they were writing the operating system in assembly language and found that that was, exceedingly tedious and boring. So they decided, well, let us just write a scripting language or a macro language to make the process a little bit easier. And that's, basically turned into the C programming language. Okay. I did not point this out before, but I do want to point it out now. There is a book called Rope Long Enough to Shoot, and then it has to do with the C language. Here we go. There's actually a book written, on this very same subject matter. Enough rope to shoot yourself in the foot. Rules for C and C++ programming. Okay, so you might want to kind of think about. I'm not asking you to read this book or even buy this book. If you look at the rating, it's not really that good. But the fact that somebody spent the time to write a book like this means the C and C++ programming languages has all kinds of traps, okay, that novices and beginners can fall into. So you kind of want to keep that stuff in mind when you move on to the next class. This may not be a good book to get, based on rating, but it does give you an indicator that this is not exactly a beginner's programming language. Okay, we used to use Pascal as a beginning programming language, and that to me is a much safer programming language because it doesn't have a lot of traps. It's very tedious. Certain things that you can do in C in one single statement, you have to do a whole lot of operations or statements in Pascal, but it is a much safer programming language. So I just want to point this out, and now that we know it, we'll move on and continue to talk about our conditional statement. And before we go any further, I want to point out where you can find your homework assignments. And you can see that in the upcoming events, and you should see exactly the same thing even on your screen when you log into Moodle. Assignment and LibreOffice is already due. Okay, so right now it is past due already. Last time I checked, 49 out of 54 students have turned it in already. Okay, and of the 54 students, one is a fake student, that is myself, so there are actually only 53 actual students. The 4 students who have not turned in the homework assignment at that point have not even logged in yet. So, everybody who logged in, have already done the homework assignment, and I'm going to pass the row sheet so that you guys can start putting your initial next to, in the column for today. Right. All right, so let's take a quick look at assignment 2, which is about assignment statements and conditional statements. Follow these instructions carefully or you may not receive credit. Download this file. This file is the one that is a hyperlink. If you don't like the theme that I have selected, you can actually pick your own theme in Moodle. Okay, It is based on each course, so each instructor can set up the rules differently. But in this class, in this particular course, you can actually pick your own theme. So if you want to pick something else, you can do it. Okay? Does anyone want to learn how to pick your own theme because you want to make it look better? Yep. Okay. Okay. So what you do is you click your own name, at the upper right-hand corner. I'm going to do a right-click and open a new tab because I don't want to lose the assignment page. Okay. So once you get here, you can go to Administration and go to Edit Profile. And once you get there, I think there's a preferred theme is, what you can pick. Unfortunately, it doesn't come with a browser. It doesn't give you a quick preview of all these different themes. I'm pretty sure you can go somewhere online, and actually see a preview of all of these themes. Right now, I think I'm using Formal White, okay? But you can also pick some other ones. These are the standard ones that are already installed. So let's pick Afterburner and see what happens. So you just click Update Profile, and you can see the theme has now changed. It's now changed. Let me just refresh the screen. So this is our new theme. You can see the highlight for hyperlink is back. Okay, so it's really just a collection of cascading style sheets and bitmaps and whatnot, and that can kind of change the look of your website. Some instructors can lock a course down. In other words, you have to use a particular theme. I leave mine open so you guys can just change it to whatever you want. Now, you might be there are certain themes only for disabled students, which means the font is exceedingly big and it's only black and white. So you might want to be careful when you're playing and know which one was the original one. You can always set it back to default, which is what I select for this course. All right, so here we go. We have a file to download. I always right-click and use Save Link As, because this way I have some control over where the file is saved. So I'll just go ahead and save the file. And once it is saved, I click the file and it will open it with LibreOffice. That's assuming you have LibreOffice already installed. If you have the portable version, that's not going to work. Okay, that's okay. That's just trying to rescue one of my other files. And it's locked for editing. To open it because I just want to open this one for this is your new homework assignment. I always put the algorithm into sheet 1, and this is what you need in order to trace the algorithm. The trace itself should be in sheet 2. So instead of alternating between these two particular tabs, the easiest way to do this is usually the same thing that I do in my classes. You go to Window, and then you select New Window. And what this is going to do is to open up two views of the same document at the same time. And you can have one to look at the algorithm, and then have the other one to focus on the trace. Now I know at this point it seems really silly because the algorithm is very small and the trace is going to be even shorter. Okay, in this case it's going to be even shorter. So it seems like I can put the algorithm and the trace on exactly the same sheet, and we don't have to go through the trouble of opening multiple windows. But I want you guys to do this anyway because later on our traces will be far longer than what it is now, even though the algorithm will stay kind of about the same length. Okay, so I want you guys to get used to this particular practice of doing things this way. If I look at properties, you can see it is created by me, and as I make changes to it, it will also say it's modified by me. When you do your homework assignment, when you save the file, after you save the file, you want to make sure that the modified has your name on it. Okay. Somebody told me that LibreOffice Portable does not save the name correctly when it's modified. Can anyone tell me one way or another? No? Okay. All right. So that's basically what I'm looking for. you just have to go through this trace using the same convention that we use in this class. Any questions about your new homework assignment? No questions? All right.
So
Yep.
which portion are we going to submit? We're going to submit our trace correct?
You're submitting the entire file. This is a single file. It just has two portions. One portion is the algorithm. The other portion is the trace.
It doesn't matter whether we annotate to save on the second sheet or the first sheet. It's still the same document.
It is the same document, correct? Yep. In other words, if I make any changes here, you can see, the save symbol is lit up. You can click save in either one, and it's saving to the same file. So it doesn't matter. It's just two different views into the same document. All right. So I'm gonna leave this one to you guys, and it's due in a week. Okay, let me just kind of go back to the homework assignment so you can see when it is due. The due date is Thursday, September 12th, so that's 1 week from today. I think you guys have more than enough time to do this, in a week. So it's just a matter of getting to it, getting it done, and uploading it. It's not going to be taking you that much time. All right. So that's your new homework assignment, and this is I just demonstrated how to change your preferred theme, and now we're back to conditions. Unfortunately, the theme does not apply to the notes here because this is actually done outside of Moodle, and this is done actually a little bit before I started to use Moodle extensively. So it's done using some other tools, which has advantages as well. All right, so we are done talking about comparisons, and now it's time to go back and talk about conditional statements. I think we talked about this algorithm already.
Yeah.
And I think we also talked about the picture already. Have we started to talk about logical operators?
No.
No? Okay, well, let's start to talk about logical operators. But before we talk about logical operators, let me use mousepad, which is a notepad basically, to show you a new problem, a problem that I want to solve. And that becomes the beginning of the explanation of logical operators. So this time I am given 3 variables, and the variables are named w, x, and y. Find the maximum and store that value, the maximum value, in variable z. Okay? You don't have to write it down because it's actually in the notes as well. So this is my new problem. Okay, I know how to deal with 2 variables already. Now I want to deal with 3 variables. There are several ways to solve this problem, some more efficient than others. So I'm going to choose a particular way to do it. Okay, because if I have 3 different, potentially different variables, each one can be the maximum, okay, depending on their values. So I know whatever I'm going to do, I need a conditional statement or something that looks like a conditional statement that we have seen before. We also know that in some cases, w is the maximum of the 3. In some other cases, we know that x is the maximum of the 3, and in some other cases, y is the maximum of the 3. So we have 3 potential branches. So the question now is, how do we structure a conditional statement so that we can get to the correct branch at the right time? Okay? Drinks. Sorry. All right. So the first thing we want to do is to say, well, let's just focus on w. Okay, let's just focus on this particular branch. How can I know that w is in fact the maximum, and therefore I need to make z the same as w? How would you express the condition that confirms that w is the maximum of the 3? Okay, w is greater than x and w is greater than y. Okay, that's a very good starting point. Okay, but let's go ahead and just do that part here. Okay, so we say if w is greater than x and w is greater than y, then we do that, okay? We have some other stuff here and some other stuff here, and this is the end of the entire conditional statement. So I'm going to leave it like this, incomplete for the time being, because I want to get back and talk about this word here, okay? And you pick the right word, okay? This is the right operator. It's called conjunction in programming, okay? It's just a fancy word for the English word and. But in mathematics and in programming, we define logical operators in a fairly rigid way. We don't just say, oh, something and something means the whole thing is true when both sides are true. Okay, we do something like this. A conjunction is an operator that has two sides, just like addition, multiplication, and so on. The entire expression is true if and only if both sides are true. Now that is different from saying the expression is true if both sides are true. Okay? In other words, the word if is not the same as the phrase if and only if, which is also not the same as the phrase only if. So those are all distinct. They're all slightly different. We can talk about that later. But for the time being, we'll go ahead and finish this particular slide. In English, a conjunction is basically the word and. The mathematical symbol is like a TP or an inverted V. In C and C derived languages, the conjunction operator is ampersand, ampersand. So this is not a typo. I did not accidentally type ampersand twice. This is the actual operator in C and C++ for logical and. So here's the question. What if you forgot about double ampersand and typed a single ampersand instead?
Something else.
It is something else. Exactly. It is not wrong. Okay? Syntactically speaking, a single ampersand is still a valid operator that can be between two expressions. But it is no longer a logical and, it becomes a bitwise and. Okay? A bitwise and a logical and sometimes will give you the same result, other times not. So you have to be very careful, because there are times where logical and will give you a result of false, but logical and will give you a result of true. So if you pick the wrong operator, your program may appear to work most of the time, but there will be certain times when it does not work correctly. It will be very hard to find these problems. And the worst part about using the wrong operator is it also depends on the compiler. You can write a program in, let's say, using Microsoft C++ or C# compiler, and it works just fine, even though you picked the wrong operator. But when you try to compile exactly the same program in GNU-C, it can behave differently, because the behavior of logical and leaves a lot to the implementation. So the implementation can change, whether by picking the wrong operator, it will do the right thing or not. In other languages, more sane programming languages, it is simply spelled out as and. Okay, so that includes Pascal, which nobody uses anymore, but SQL and Visual Basic are still fairly common. So those programming languages still just use the word and to mean conjunction. The definition of conjunction is, you can look at the definition like this. True and true is true, false and true is false, true and false is false, and then false and false is false. This is not something you can do with arithmetic operators. Can someone enumerate all the possible combinations for addition? In other words, you would define addition as 1 + 1 = 2, 1 + 2 = 3, 2 + 1 = 3, 2 + 2 = 4, and so on. How long would that list be? It will be an infinitely long list, okay? Because there are an infinite number of values. But in a Boolean operator, this is called a Boolean operator, each side of the conjunction can only be true or false. Okay? So you have true or false on one side, you have true or false on the other side. How many possible combinations can you get? 4, right? Because when this side, when your left-hand side is true, your right-hand side can be true or false. So that's two combinations. When your left-hand side is false, then your right-hand side can also be true or false. So that's two additional combinations for a total of 4. And that's why with logical operators or Boolean operators, we can just define an operator like this, spell it out completely. Is that okay so far? Okay. Next, we move on to disjunction. Disjunction is basically the English word or, but not either or. Okay, so this does not mean the same thing as either or. It's just a regular or. This operator also has two sides. The entire disjunction expression is true if and only if at least one side is true. So when you look at the definition, that actually reflects what I just said. True or true is true because at least one side is true. False or true is true because one side is true. True or false is true because one side is true. False or false is false because both sides are false. We don't have a single true on either side. Are we doing okay so far with disjunction? It really is the same way that we use the word or in English. It's just more formally defined. The mathematical symbol is like a V, but it's not exactly a V. If you use a word processor like Microsoft Word, there are ways to input that particular logical operator. In C and C-derived languages, this is a typo here, derived, not derived. It's a double bar. Okay, it's bar bar, and once again, if you use a single bar, it becomes a bitwise OR instead of a bar bar, which is a logical OR. And then once again, the result can be different depending on which one you're using. I think with an OR, they mean about the same thing. It's close enough that you won't be able to spot the problem most of the time. In Pascal, SQL, and Visual Basic, the operator is simply spelled out as OR. Are there any questions about the operator called disjunction? Okay, disjunction is or, conjunction is and. The next one is even easier. This one is called negation, which is a fancy word for the word not in English. This operator only has one side because you can only negate one value and then get the result. The negation expression is true if and only if the value of the right-hand side is false. That's the only time you get true. For all other times, which is the only other case, it will give you a result of false. The mathematical symbol is a little bit hard to see, from your perspective. It's like a little cliff. It's a horizontal line with a drop off, like a cliff. In C and C-derived languages, the operator is an exclamation point. In Pascal, SQL, and Visual Basic, the operator is spelled out as not, not. Okay, and there are only two possible combinations because you only have one side that can have a variable value. Not true is false, not false is true. And that's the negation operator. Are there any questions about the three logical operators that I have just mentioned? No questions? That's okay? All right. So now we can get back to the program, and we can try to finish up this algorithm here. Okay, so let's say W is greater than X and W is greater than Y is false. Okay, well, if that is false, that means W is not greater than the other two variables. So it cannot be the maximum. So we think. Okay, there's a little flaw in this reasoning. But let's just think in that line, and then later on I will point out an example where, oh, so that's why it doesn't work. If I can just follow the same logic here, I can say, oh, if this expression is false in general, let's try something else. Let's try to see if we can confirm X is the maximum. So I'm going to use the same pattern here. This is not the most efficient way to do it, but it is one of the more intuitive way to do it because I'm just repeating the same pattern over and over again. So in the second condition, X is greater than W and X is greater than Y, that seems to confirm if that expression, if the entire conjunction is true, it seems to confirm that X is the maximum of the three, and therefore Z which is going to store the maximum, should be updated with the value of x. Is that okay? So that's kind of my reasoning at this point, but it is flawed. Remember, it is a flawed reasoning. It's just flawed a little bit, not a whole lot. If w cannot be confirmed as the maximum and x cannot be confirmed as the maximum, since I only have 3 variables, y has got to be the maximum. So in the last one, I just say else. Okay, so this is called a multi-branch conditional statement because unlike a conditional statement that we have already talked about, this one has got 3 branches instead of 2. Okay, so for anything that has 3 or more branches, we just call those multi-branch conditional statements. Only certain programming languages have constructs like this. In C, it seems like it has constructs like this, but it's not really the same thing. Okay, it can syntactically look like this, but it's not the same thing. All right, so let's take a look and let me think about the ordering here, because I want to point out the flaw of this program, but I first need to show you the exact way of evaluating the conditions, because it seems to me that I can evaluate this condition first. If that is not true, then I can evaluate this one. If both are false, then I go ahead and perform this operation, but that really is not the case. You have to evaluate the conditions one by one. Evaluate this one first. If this is true, you execute this statement and you're done with the conditional statement. If you evaluate this condition and the result is false, only then you should evaluate the second condition. Okay? But that's kind of vague. Okay? When I mention things like that, it's kind of vague and not so easy to understand. So we're going to do this in a visual way. Just like last time with a regular conditional statement. The picture is already in my notes, but I just want to kind of do this interactively. So this way we can kind of keep an eye on the picture itself. All right, so here's my Inkscape program, which is really useful for many other purposes too, but for this class I'm just going to use it for the purpose of drawing pictures. So I'll use a pencil tool to look at the entry point of a conditional statement. Okay? When you're programming, every branch should only have 2 ways to proceed, not 3. Okay? So the apparent 3 branches of this particular multi-branch conditional statement cannot be the result of one single branch. It is the result of 2 branches. And this is how we structure the 2 branches. In the first branch, okay, it branches out like, oops, undo. Okay. It branches out all the way like this, and then we specify the operation, in this little box here. And this is our operation of z. And it's using a small font. Let me pick a bigger one. Okay, this is z. Okay. And it's changing the font back. Z gets the value of w. Okay, I'm using less than and a dash to kind of approximate the left arrow symbol. Okay, so this is our first branch. The second branch is actually down here somewhere. Let me continue with this picture. So if the first condition is false, I'll be forced to get to the other side. But the other side is not a straight branch either, because it is its own, it's a branch on its own. So let me try to draw that branch. So here are our 2 additional branches. This one is z gets the value of x. This one is z gets the value of y. And after each branch, they all merge. So the merge is kind of like all the way down here, but they all merge together when each one is done. Oops. There we go. So this is what the multi-branch conditional statement actually looks like. Okay, there are two forks. The first fork has two possible ways to proceed. The second fork also has two possible ways to proceed, for a total of three possible ways to proceed. Okay? But every time we have two ways to proceed, we have a question, right? Remember, we need to ask the question whenever we have two ways to proceed. In this particular case, the first one, I need a little more space because the condition is actually longer in this case. It would be W is greater than X and W is greater than Y. And this branch is labeled true. This branch is labeled false. So are we doing okay so far about the first decision point? Okay. You answer the question, W is greater than X and W is greater than Y. Is it true or is it false? If it is true, you follow the left-hand side, you perform that operation, Z gets the value of W, and what do you do after that operation? You get all the way out of the conditional statement. You do not evaluate any additional conditions. What about the second branch? The second branch has its own question to ask in order to determine which way to go. And that question is very similar to the first one because I intentionally picked something that is symmetric. So the second question to ask is X is greater than W and X is greater than Y. Is that true or false? And then it's the same way here, I label the one on the left true, label the one on the right false. And that really is the structure of the conditional statement. We have the pseudocode on this side, and then we have the pictorial representation on the other side. Are there any questions about how the pseudocode on the right-hand side corresponds to the pictorial representation on the left-hand side? Any questions about why we cannot exchange the order of evaluating the conditions? We always have to evaluate W is greater than X and W is greater than Y first because that is the first question that you encounter. Is that okay? Okay. So after this is explained, now we understand the behavior or the expected behavior of this code. Remember I said this logic is flawed? Okay, I said it was flawed. So let's figure out why it was flawed. Okay? But this is a good exercise. It's a good exercise because it kind of illustrates how do you know an algorithm is incorrect? That's the question. How do you know an algorithm is incorrect? I think I brought this question up last time already when we were simply finding the maximum of two variables. But in this case, it gets tricky because this one is actually wrong, okay? But it is only wrong when you feed it certain patterns of values. Okay. So we'll do something that is kind of boring or seemingly boring first. So what I'll do is I'm going to write the algorithm in my spreadsheet. So I say, if W is greater than X, and W is greater than Y, then make Z the same as W. Else if X is greater than W and X is greater than Y, then Z gets the value of X. Else, Z gets the value of Y, and if. Okay, so that's my algorithm. I use indentation to indicate, what is contained in what else. We'll get to, the whole point of indentation later on. But for now, we just focus on the pseudocode, and I think that's a little bit too big. And then we open a new window to look at the first trace. Okay. And this will get a little bit boring because that is one of the points that I want to make. Not that programming is boring, but the point is it is difficult to find a case where the algorithm will fail. If you just take random shots, with test cases to see whether the algorithm is incorrect or not, it might take you a long time before you throw one dart and it lands on the spot where it will show the algorithm is incorrect. Okay? So I do want to kind of emphasize that. And so we will have test cases that cannot find the flaw of this particular pseudocode. We have comments because we have conditions to evaluate. In fact, comments will take up more space because my condition is kind of long in this case. And then we have line number. We have the 4 variables because we have W, X, Y, Z as our 4 variables. And we'll go ahead and make certain assumptions. The precondition in this case is, let's say just 1, 2, 3, and then Z has an unknown value. Z doesn't need a known value because we always overwrite Z. Regardless of which branch I take, I'm guaranteed to modify the value of Z. So why do I need to make any assumption when I'm going to overwrite it anyway? All right. So now we proceed with line 1. We have to indicate the result of the comparison in the comments column. W is greater than X, and W is greater than Y is false. Okay. We proceed to line 2. Oh, we don't proceed to line 2. Where do we go? Line 3. No, we proceed to line 3 because the first condition or the condition on line 1 failed, so we have a second chance on line 3. We want to check whether the condition is true or false on line 3. Okay. So line 3 is saying X is greater than W and X is greater than Y. Well, that turns out to be false as well. Then where do we go? We go to else. Okay, so this time we go to line 6, which is the else case, and then we copy the value of Y, which is 3, to variable Z. So Z is now 3 also, and we are done with the trace of this particular test case. Are there any questions about the behavior of this particular trace? Yep, go ahead.
When you say pre, that's what's that again?
That's a precondition.
Preposition.
It's a precondition of the entire algorithm.
You just pick 1, 2, 3 because of what?
Because this is one test case. In other words, if I suspect this algorithm is incorrect, okay, so it's almost like this. Okay, so let's say all the possible combinations of x, y, w, x, and y is like this square here. Okay, so the area inside the square represents everything that I can possibly throw at this algorithm. Okay, in some cases, this square is infinitely large. Okay, but in programming, nothing can be infinitely large because even with integers, we only have a certain range, but it can be very big. So let's say this is representing everything that we can throw at it. The cases where the algorithm will fail can be just a line here. Okay, so the green line is representing the cases where this algorithm will not work correctly. But everything else, okay, if you look at the entire square, just minus this line here, everything else, it will work correctly. Okay? So my point is, just imagine that you're standing back here, and then you're just throwing dots, okay, in the dark. And you're trying to see whether the dart will hit the green line, so you can see, oh, okay, the algorithm was actually incorrect. Okay? Are you seeing the analogy? No?
But let me just say this. When I look at the left side program and there's no values given.
Correct.
And then when I see that precondition and you just throw 1, 2, 3, I'm like, where do you get the values from?
They are just given to you.
Okay.
Yeah, they're basically given. So if you have a program that relies on certain given values in order for it to function, just like this one, I need to give you a precondition.
Just to do when it gets to the end and see the program work as it's written.
Right.
Okay.
And so I don't have to change the program for different test cases, because otherwise I would have to change the program in order to handle different test cases. Yep.
I have a question. You in your line tracking, your line number tracking.
Mm-hmm.
So you started at 1 to say that it was false.
Yep.
But then you went in your 5th row. You went to line 6.
You mean here?
Yeah.
Okay, let's take a look at the picture. because the picture actually helps to illustrate the whole thing. Let's see. Okay, so what I'll do is that's not showing really well because the picture is now too small.
Well, my question is, you went with line 1 and then with line 3, but then I guess line 5 and 6 are the same then, you're saying?
No. 5 is the old statement. You don't evaluate one. There's nothing to.
There's no evaluation. Okay, thank you. Okay.
Oh, okay, I see your
That
question.
clarifies it for me.
That's the problem.
Okay, because I'm, it's.
So if there was another evaluation in 5, then you would go to line 5, but because there's not, 6 is.
Line 5 is never tracked because it doesn't do anything. The word else,
you.
doesn't do a single
Okay.
thing, so we don't track that.
Okay.
Nor do we track and if because it also does not do anything.
Okay.
Those lines, line 5 and line 7, they exist purely for the purpose of separating different parts of a construct.
Okay.
And as a result, they don't do anything. On the other hand, line 1 and line 3, even though they also serve the purpose of separating different chunks, of the same, construct, but they also do something. They also have a condition to evaluate. And any line that actually has something to do, I have to track in the trace. That's a good question. Yeah.
What about line 2 and line 4? They had in that particular one they have an assignment.
Yes,
Yeah,
line
but
2 and
it
line
could be
4
done.
are not tracked in this case because we never get there.
Oh.
Okay. Now let's take
Oh,
a
I
look.
see.
I'm not sure how
Yeah.
well you guys can see, the picture here, but you can see the general shape. Okay, so we can just look at the general shape of that picture. There's no way for me to. I may be able to remove these tools. Yeah, I can just get these out of the way and give myself a little bit more area to look at the picture itself. Slightly better, not a whole lot. Okay, but this way I can actually show you, line by line, where in the picture is what in the pseudocode. Okay, this is before line 1. Okay, where I'm pointing at right now, that's before line 1. Line 1 is representing this junction here. It is the first fork where we have to make a decision and say, okay, do we go left or do we go right? Okay, that's line 1. But in order to make that determination, we have to answer this question. W is greater than X and W is greater than Y. Is that true or false? Because that answer will guide me to one way or the other. In this particular case, because W, X, and Y have these specific value, 1 is greater than 2 and 2 is greater than 3. Oh, excuse me, 1 is greater than 2 and 1 is greater than 3 is false. Okay? And that's why I follow this branch here. And that's why we don't track line 2, because we are actually going in this direction. And this becomes my line 3. Right here, the second junction becomes my line 3, and that's why in the trace here we track line 3. Line 3 is asking the question X is greater than W and X is greater than Y. That expression is also false because X is 2 and 2 is greater than 3 is false. So that's why we follow the false branch here. So we end up here eventually, and this line here is actually our line 6, and that's why the next line to execute is line 6. Okay, so there's a lot of stuff going on. The first time you see something like this, you have to look at the pseudocode. You have to look at the picture representing the pseudocode, and also from those two, you can then decide, okay, where do I go next? Are we doing okay so far? Okay. Yep. Go ahead.
You're saying that it's wrong.
The algorithm is not always right. Okay. But as far as computer science is concerned, if an algorithm is not right all the time, it is wrong. It is incorrect.
Right. It's just like your positions.
It's
If it's true and true, then it's true.
you don't want a program that works most of the time.
Right.
You don't want your anti-lock break system to work most of the time.
So is there a way to restructure the algorithm so that it's right all the time?
Yes, but we can only do that after we identify why this one is wrong, or the fact that this one is wrong. Because if you just look at the algorithm, it looks right. And we can throw a lot of test cases at this, and it will still behave correctly. Yep.
What if W is 2 and X is 2?
That is the only case, and Y is 1. Okay? So it takes a very specific test case to find out this algorithm actually doesn't work all the time. Okay? So let me just go ahead and copy and paste it. I just want to show you a few more test cases just so that you guys are convinced that this algorithm is not going to it's not easy to spot that it has a problem. This is my second test case. The precondition is x, w has a value of 2, x has a value of 2, y has a value of 3. It doesn't change the flow of the algorithm. Okay, it will still move in exactly the same direction, because if you look at the first line, look at the first condition here, this will still be false because w is greater than x is false already. Okay, because they are the same. And then you look at the one on line 3, x is greater than w, it's also false because they are the same. And so based on that, we'll get to line 6, and z will still end up with a value of 3, which means the algorithm is still quote-unquote correct because it's still doing quote-unquote the right thing. Okay, so let's take a look at the next test case. I think you guys are starting to get the point here. So I'm going to end this with this. The algorithm will do the wrong thing and say that, hey, y is the maximum. It has, because x is greater than, w is greater than x is false, and also x is greater than w is false. That basically turned the conditions of line 1 and line 3 into false statements. And then you have no choice but to go to line 6. But in this particular case, the maximum is actually 2. So it's wrong. In other words, this is representing, this is a very small number of cases compared to the entire space of all the possible values. Which also means, if somebody is to test an algorithm just by throwing, test cases at it, the chances of finding this accidentally and say, oh, you know what, we cannot release this particular program because the algorithm is incorrect, that chance is really slim. So somebody will release software with this code here, and only very occasionally it will find the wrong answer. And then the software will do something it's not supposed to, and bad things will happen. Okay. Do we have any questions about this particular example, or about this particular test case and why the algorithm is behaving incorrectly? So how do we fix it? There are many, many ways to fix it, but the easiest way to fix it is like this. Turn the greater thans into greater than or equal to's everywhere, and that will fix the problem. Not the most efficient algorithm, but it will fix the problem. Because if w is greater than or equal to x and w is greater than or equal to y, guess what? W is the maximum. The one test case that failed the previous algorithm would now work correctly. But once again, how do we know this one will work for all test cases? All I did was to fix the one that I found last time. How do I know that by fixing that problem, I'm not introducing a new problem? No, we do not. The only way you can know for sure is to prove the algorithm is correct step by step, line by line, using math. Okay, so it becomes a math proof. How many people have taken algebra or one math class that requires proofs? And how many people enjoy that process? Okay. Significantly fewer people. But that's what you need to do in order to analyze an algorithm and say, okay, I know this algorithm is correct. Okay, because otherwise, you can end up with an algorithm that works most of the time, and the algorithm that works most of the time are worse than algorithms that do not work at all. Because people end up releasing the software, and depending on where it goes, when it fails, certain times, well, it only affects one person, it's an annoyance. Other times, people can die. Okay, so my personal selfish, motivation to teach this class, in the way that I think is right, is to make sure that whoever writes the software of my pacemaker, my will-be pacemaker, understand all these concepts and do not make simple, stupid mistakes in that software, in my pacemaker. So that's that's completely out of a selfish personal motivation, but it's a good reason. Because the pacemaker may be comparing three different things and choosing the maximum of the three, and to determine whether it wants to give my heart a pulse, and if it's doing the wrong thing, it may give my heart a pulse when it's not supposed to, or not give the heart a pulse when it's supposed to. Either case would be bad for me. All right, so that's this stuff is all in the notes too. Okay, it's all in the notes. There's nothing really new, compared to what is already typed up in the notes. Because what we are doing is here, back to the example. And here you see exactly the same algorithm, and also a particular test case, to show that it is working correctly. Okay, so as I said, nothing really new. And then the else if thing is kind of interesting. This is a picture, a general picture of a three-branch conditional statement. I'm not going to talk about how to do this in C, just yet, because I need to talk about nested statements first. Then we can go back to this example and say, well, since in C we don't really have the construct of else if, so what do we do when we have to express a multi-branch conditional statement? So we'll I'll defer that topic until we are done with nested statements. All right. So now we can go back to the main topic and move on to loops. Yay. Just right click. It's not showing anything. That's a little annoying. Hmm?
That worked for me.
I think it might have something to do with me changing my theme. Okay, let's change it back. And by the way, that penguin is the kind of like the mascot of Linux. Tux. Yeah. But that's a cute version of Tux. There are different versions too. Okay, let's see whether that works. No! Okay. This is annoying. Alright. I can fix that. Here. Part of the reason is because it's opening up in a separate window. So I go to Appearance and we just say open without being the same frame and save and return. Open. Alright, let's try. Tab. Yay, that worked. Okay. All right. So far, yep, go ahead.
One more time. We can make any precondition, pretest, or any test data we want as long as the trace is true. Is that what you're saying? you said 1, 2, 3, we could put in 6, 7, 8 as long as it comes out to be true at the end.
Not as long as, it's really all you're doing is you're stating the precondition. So that particular trace is representing what if these variables start with these particular values. Now, whether it will get to the right, conclusion is entirely up to the algorithm. Okay, in fact,
But as long as it follows the logic of the program written, is what I'm saying.
yes, as long as
We
it
can pick
follows
any
the logic.
precondition. We can pick any numbers we wanted to, as long as they.
Correct.
Okay.
Because there are certain algorithms that make certain assumptions. Some search algorithms will assume something is already sorted. So that means you cannot give the algorithm something that is not sorted because it is not going to work. The algorithm has to make assumptions. So that's why you have to state your precondition according to the confinement of what the algorithm is expecting. Now, in the algorithm that we just talked about, finding the maximum of 3 variables, I do not have any particular restrictions. I don't have to say, oh, the first one has to be larger than the other 2. So I don't have any restrictions. That's why I can throw any value into those 3 variables when I'm testing it.
And you just wanted the largest one to be the last one, so it'll go all to the whole program.
That's the one that basically broke the program. If I have 2, 2, and 3, and do not change the greater than to greater than or equal to, that broke the algorithm. Or, I should say, the algorithm went through, but the end result was incorrect. 2, 2, and 1, sorry. When I have w and x both equal to 1, but y equals, excuse the other way. When I have w and x both equal to 2, and then y equals to 1, that's the case, when the original algorithm, the incorrect one, will be incorrect. Gave me the incorrect result. All right. So let's talk about loops. What is a loop? Well, a loop is, very simply put, our last control structure. Okay? There are only very few control structures. One control structure is a sequence, which means we just do things in the right order, in the same order that it is specified. The second one are conditional statements. We get to a certain point, and there are 2 ways to proceed. We use a condition to tell us which way to go. But the thing about a conditional statement is, it doesn't matter which way you go, but they all converge at the end, and then you have to get out. So before we talk about this, we do not have any ability to do something again and again. Okay? Is it important to be able to specify the logic to do something again and again? Do you do something on a daily basis that has basically repetitions built into it?
Yes.
Okay, give me one example.
Logging in stuff, loops, those are loops. We log into like password, we log into like your bank account online.
Okay. I'm hoping that it's not a loop, because a loop kind of implies that you fail and then you have to try again.
Yeah, when you fail, it
Yeah.
loops.
Well, I can give you one example. Before the parking structure was up, finding a space to park was definitely repetitive, right? You just keep circling around and around and around until you find a parking spot, right? So that's repetition. So even in our daily activities, without even taking computing into consideration, we do a lot of stuff that is repetitive. And as it turns out, this is also very useful in algorithms. In fact, I would say this is the most useful control structure in programming. Even though conditional statements are useful, this one is even more useful because you can find it even more in more algorithms. Yep, go ahead.
Well, now, you use the analogy of the parking situation for the structure. Isn't that more of an if-then rather than a loop? If it was a loop, you'd still be driving, correct?
If it is an if-then, that means you go through the parking lot once, you cannot find a parking space, you go home.
No. Then you drive up one row, no parking, then you go to the next row.
Okay, but what if you have driven through all the rows that you have specified?
Now it does repeat.
No, it does not repeat.
No, but if you don't find a spot, you go back and you keep searching the.
But that's a loop now.
Doesn't a loop imply that there is no end?
A loop can possibly have no end, but that's not the attribute of all loops. Yep.
I think I have an example in using your password. So a loop specifies it must see X digits and must be in this certain sequence to allow you to move to another page. So you put in an incorrect sequence or an incorrect password. It is not the correct criteria to exit the loop, so it stays within the loop, goes back up top, gives you a new screen with a blank attempt, and allows you to attempt it again. Until you enter the correct password, will it let you exit the loop.
Or you press the cancel key, because the loop can check for that condition too. Okay? But let me just kind of get back to the parking lot thing, because when you use conditional statements, what is a conditional statement? Every conditional statement looks like this. Okay? 2 ways to proceed. But the 2 ways to proceed eventually will merge. Okay? You have an entry point, you choose one side to go, and then you exit. All right? So in a parking situation, you can say, if I can find a parking space, in the first aisle, okay, I'll park my car, and then I will go to my class. No problem. If I cannot find a parking spot in the first aisle, I'll turn to the second aisle. Okay? Now this is actually forcing me to get into nested statements, but it's okay. Because if you're turning into the second aisle, what if the second aisle does not have a spot to park? Well, then you have to, in this case, you're gonna park your car in the second aisle anyway. You're gonna block some car, right? Because it doesn't have a provision to say, but what if the second aisle doesn't have a spot? Okay, so if you want to express the logic of what if the second aisle does not have a spot, that means this by itself is going to be a conditional statement, a little conditional statement inside here that says, if the second aisle has a spot, I'm going to park my car, and then I'll proceed and walk to my classroom. But what if the second aisle does not have a spot to park? I'm going to go on to the other alternative. So you can kind of imagine this thing has its own little conditional statement, and the smaller one, and smaller, and smaller one, like the Russian dolls, right? Okay. Okay. It's like the Russian dolls, where you take out one, and then the smaller one inside, take out the other one. There's a smaller one inside. But this cannot go indefinitely. Okay. It cannot go infinitely small. At some point, you will have traversed the entire parking lot and not find a spot to park. Okay, so it'll be down here, somewhere, right here. Okay, so at that point you say, there are no parking spots. So what do? You cannot go back to the beginning. Okay, there's no provision to go back to the beginning in a conditional statement. So even though I have tons of conditional statements embedded into one another, none can go back. They can only go forward.
Now, I'm sorry to beat this dead horse, but if you have
It's okay, we like doing that.
If you have a line that says, the first one says drive down aisle 1, okay? If you find parking, and if not, continue to line 2. If not, continue to line 3, and so on and so forth. You get to the end of the parking rows, and you still don't find a parking spot. You can't write something there that says, if there's no parking spot in row Z, return to line 1.
Okay, now you're talking about the taboo statement in programming. You're talking about go to. Okay? Do not, never, ever use the G word in programming. Okay? Because you are correct. There is a way to only use conditional statements to emulate what we call structured loops. Okay? It is possible, but it is a taboo in programming. We do not do that, but for good reasons. Okay? Because the use of go to, the statement that allows you to go from any place within your algorithm to any other place within the algorithm, is dangerous. Okay? Because if your program is starting to have more and more and more of statements like that, it becomes what we call spaghetti code. Spaghetti code, if you just look up on Wikipedia, Getty code. And Wikipedia has an entry for that because it is a fairly common phrase that people use in programming. And spaghetti code is a pejorative term for source code that has a complex and tangled control structure, especially one using many go-tos, and so on and so forth. Okay, and when you use a go-to, you might feel, hey, this is an easy solution to a fairly complex problem. Okay, and then you use it again, and then you use it again, and then you move on to a different job. I feel sorry for people who have to pick up after your programs because they will have a hard time following the logic and fix any mistake that you might have put into the program. Okay, now how do I know that? I have done it. Okay, there was one single algorithm in the subroutine, but we haven't talked about subroutines yet, so no, I'm going to talk about subroutines. But just look at it as one single algorithm. It's 500 lines in C, and has go-tos all over the place. Okay, I could not follow the logic of that subroutine, so what I ended up doing was I chucked the entire subroutine, and then I just rewrote the entire thing in 20 or 30 subroutines. So that's why go-tos are really bad. It's really hard to say why it is bad because you guys, at least in this class, you will never write any programs that will be long enough and complex enough to realize how bad go-tos are. Even in your other classes, you might have programs up to 500 lines, 700 lines. And having go-tos in those programs will still not be a big thing because a semester is only 3 months. Okay, you don't have to get back to a program that you wrote 2 years ago and say, what am I doing with these go-tos? So just don't do it. If you use go-tos in your other classes, like in your C class or your Visual Basic class, you'll get points deducted for sure. Okay. Yep. That's why we call that the G word in programming. It's big taboo there. Big, huge taboo.
I swear there's legitimate uses for it.
Yes. There are almost no legitimate use of go-tos.
I saw one.
You saw one?
I saw one once. It was great.
Was it emulating a normal loop structure?
No,
mean?
never.
No. There are very, very few cases where go-to is warranted. Sometimes you can use an exception to kind of get your way out, when something really bad has happened and there's no way to proceed. So instead of using a go-to in C and C++, you can use an exception to deal with that. So anyway, so when we're talking about loops here, we're talking about structured code. Okay. Now, structured code is a very important concept. We'll talk about that later after we talk about what a loop is. Okay. Let me go back up to the previous level here. There are 2 types of loops here. I'm going to kind of talk about this in a slightly different way than it is presented in the notes, but it's the same material. Because I want to change the order and talk about while loops before we talk about repeat loops. Okay, because while loops actually makes a little bit more sense. Okay. So let's say we want to represent the logic of channel serving. Okay, we have all done that, with channel serving. So what is the logic of channel serving? What is prompting you to keep hitting that, channel up button?
You have found what you want, or something that interests you.
Okay, that's very good. Something that interests you. You can turn it into a condition, right?
Yeah.
The current channel that is being played, on the TV is interesting or not interesting. That becomes a condition that can either be true or false. Okay, very good. Okay, so let's go ahead and draw a picture representing that. So let's go here, start a new picture. We'll just call it data size. I'm not going to save any of these, because the whole lecture is getting recorded, so there's no need to save these documents. All right. So here's a picture, and we have let's start with the condition. Okay, so this time we'll start with a condition here that says, okay, this is a little bit too big. Change the font size, maybe 16. The channel, the current channel, but when I say the channel, it means the current one, is not interesting. There we go. Okay. Now, I understand the computer usually cannot, make that determination, but you can, right? So this is okay for pseudocode because to you, it is a statement that can end up with either true or false as an answer. Okay. What do you do when a channel is not interesting? Click that button, right? What do you do after you click that button?
Examine it again.
Evaluate the condition again. Okay, very good. So that means if this is the question that we are asking, okay, let me do something here, group it, so I can move the whole box around. If I draw a picture of this logic here, we have an entry point which kind of represents when you turn on the TV. Okay, so you only turn on the TV once, and then it shows a particular channel, and then you can start to apply this logic. So this is telling me that there are two ways to proceed. Okay, so once again we kind of draw a branch here, but this is not exactly a branch because one side is going to go back to an earlier step, and I would even label this particular branch as true. And so the other branch has to be false because one has to be true and one has to be false. Okay, so far it looks like I'm drawing a conditional statement because it has the same elements as a conditional statement. It has a condition to evaluate, two ways to proceed. One side is labeled true, the other side is labeled false. Okay, the side that is labeled true is going to lead to an operation, right? Lead to a statement. So I'm going to draw that statement box, and you guys can tell me what to type inside that statement box. What do you think should go into this statement box here?
Interesting.
Change channel, right? Okay, channel up. Okay, so we go channel up. I'm making the assumption that you don't know exactly which channel you always want to watch and can just punch in the channel number. So your remote control only has one button to change the channel. The next one. Okay. All right. Because otherwise you can say, oh, I know exactly which channel I want. Punch in the number, I'm done. Okay, but no, not in this logic here. What do you do after channel up? You have to reevaluate. Oh, so that means I have to make a hole in this portion of my picture. So this is no longer a line like this. This is now a line that looks more like this, because I need a way from this action to go back to an earlier point and say, oh, you know what? I want to reevaluate that condition to see whether the new channel is interesting or not. Are we doing okay so far? Okay. But remember, this is a one-way street. In other words, you cannot go from here and go backwards like this. So let me just emphasize, this is only a one-way street. When you look at these charts here, just remember San Francisco, downtown. It's mostly one way, or all of them are one way. Okay, so this is one way, and also one way here. You just have two possible ways to proceed. Okay, so we are starting to see a loop here, okay, because we are seeing if the channel is not interesting, we press the channel up button, but then we have to go back to reevaluate the condition to see whether we have to press that button again or not, right? So let's just say that you find that at one point the channel is what you want to watch. Okay, it's Mythbuster for me. Okay, so what do? I stop pressing that button, right? So I can proceed and make popcorn and do other things. So you have to get out of the loop. When the channel is interesting, which means the condition is false, then you have to get your way out of this loop so you can proceed with making TV dinner or making popcorn or whatever. And that's how you get into a loop, and this is how you get out of a loop. Yep.
back to where you're learning about the parking lane and stuff, you do the same thing, right?
Yep.
Instead of like how you were doing it up there.
Exactly.
Right.
Yep, this would be the proper way to find a parking space. But you might want to improve the condition a little bit. So you want to say, you know, while cannot find a parking space, try to find a parking space. But you might want to add a condition to that conditional statement. So you might want to say, while no parking space found and class time is not over. Because when class time is over, forget about finding a parking space. I'm getting out of this loop and go home, right? So you always have to kind of think about all those unlikely but possible conditions, because otherwise you'll be stuck in a loop, right? You know, if for whatever reason the parking lot, you know, is blocked, you know, because they have constructions going on, then the condition of no parking space available is going to be true for a week, a month, or whatever, right? So you'll be driving your car around until there's no gas. Then you'll call AAA to gas it up and then keep driving because the logic doesn't let you get out, right? So in a realistic sense, you have to make this condition, you know, not only to catch the most obvious case, but also to catch the unlikely but possible cases. Like in this case, you know, if the channel is not interesting, you don't always go, you know, press the channel up key, because you might want to specify a timeout condition and say, okay, if I cannot find anything interesting in 5-10 minutes, or until I have something else to do, I want to exit. You know, if I have something else to do at a certain time. Yeah. That will be the end of the program, not just the loop. All right, question?
Can you have multiple loops in an algorithm?
Oh yeah, absolutely. You can have one loop after another loop, but you can also have a loop inside a loop. In other words, this thing here inside can by itself be another loop. But that will be the discussion of nested statements, how we can put one statement within the other one. Okay? So I'll see you guys next Tuesday. Have a nice weekend. And don't forget your homework assignment. Thank you. I'm starting to see some absences.
Did anyone manage to get dropped today?